Hello and welcome back to Machine Learning. I'm Jyoti Presti, and in this video, we are going to talk about deep reinforcement learning. So let's begin. First, let's understand in the simplest way possible what is deep reinforcement learning. So deep reinforcement learning combines artificial neural networks, which we have already seen before, and it also combines a framework of, with that, it combines a framework of reinforcement learning, which helps software agents learn how to reach their goals. So we have studied before a long time back in one of the very first couple of videos that machine learning has three different types: supervised, unsupervised, and reinforcement. And reinforcement is the type of learning that happens on its own, where you just have to say this is right and this is wrong. So this particular type of learning, which is deep reinforcement learning, it combines reinforcement learning, which is a type of machine learning, with artificial neural networks that we just studied. So it unites function approximation and target optimization, mapping states and actions to the rewards they lead to. Now let's talk about what is reinforcement learning, because we didn't get into much detail of that in our previous videos. So reinforcement learning refers to goal-oriented algorithms which learn how to achieve a complex objective or a goal, or how to maximize along a particular dimension over many steps. For example, they could maximize the points won in a game over many moves. So there could be a board game like chess, or Go, or Chinese checkers, um, and other games like that. So you could use a reinforcement learning algorithm to maximize the points won by making different moves on the game board. Reinforcement learning algorithms can start from a blank slate and, under the right conditions, achieve superhuman performance, which means you don't have to necessarily provide a lot of data to begin with. Okay, you could just provide some mechanism to run, and the algorithm can learn on its own. So, like a pet incentivized by scolding and treats, these algorithms are penalized when they make the wrong decision and rewarded when they make the right ones. So, this is reinforcement. Okay. So, just like if you had a dog and if you were to train a dog, then you would be training the dog on the basis of whether or not it does what you're asking to do. So, if the dog actually obeys you, you will give it a treat. And if it does not, then you don't give a treat. And that's how the dog learns that this is good behavior and this is bad behavior. Similarly, this algorithm also is told that, this is good and this is bad, or this is right and this is wrong. And that's how it learns on its own that, if I do these things, it leads me towards something right. Now let's take a look at different terminologies that are used in reinforcement learning. So first we have the agent. An agent takes actions. For example, a drone making a delivery, or Super Mario navigating a video game. So here the algorithm is the agent. Okay. And in real life, you could consider that you are an agent. Let's talk about action. This is another terminology. So A is the set of all possible moves that the agent can make. Okay, so if you are a person, you could make different moves, like you could walk from this place to that place, you could dance, you could sing. Those are the different actions that you can do. And although action is almost self-explanatory, it should be noted that agents usually choose from a list of discrete possible actions. So as human beings, there are like infinite number of things that we can do as actions. But when we want to implement a reinforcement learning algorithm, then we would be choosing from a list of possible actions. So it is a finite list, it's not an infinite list. In video games, if you're playing, then these actions might be, turning right or turning left, or jumping high, jumping low, crouching or standing still. These are all types of actions. If you have stock markets, then you could have actions like buying, selling, holding. Okay. If you're handling aerial drones, then you could include many different velocities and accelerations in the 3D space. The next term is the discount factor. So the discount factor is multiplied by future rewards as discovered by the agent in order to dampen the rewards effect on the agent's choice of action. Let's take a look at what that means. So it is designed to make future rewards seem less worthy than the immediate reward, so that it enforces a kind of short-term hedonism in the agent. Okay, so sometimes your algorithm might start thinking about what happens if I make this move now, how will that affect me in the future? So if you want, you could add this discount factor that will make future rewards seem less important than the current ones to your algorithm. So often this is expressed in the lowercase Greek letter, which is gamma. Okay. And if gamma is 0.8 and there's a reward of 10 points after 3 time steps, then the present value of that reward is going to be 0.8 raised to 3 into 10, which is very less. Okay. So gamma is 0.8, but the reward is going to be of 10 points. After three steps, you will get a reward of 10 points. But right now, the value of that reward is just 0.8 raised to 3 into 10, which is very less. So a discount factor of 1 would make future rewards worth just as much as immediate rewards. Okay. The next term is state. So a state is a concrete and immediate situation in which the agent finds itself. So that is, it could be a specific place or a moment, an instantaneous configuration that puts the agent in relation to other significant things, such as tools, obstacles, enemies, or prizes. Okay, so it's sort of the situation of the agent at the moment is known as the state. So it could be a time related state, it could be a place related state. Okay, so it would help you to correlate that with tools and obstacles, enemies, and prizes of that particular agent. So the current situation, which is returned by the environment, or any future situation, can all be part of the state. Okay. Were you ever in the wrong place at the wrong time? That's also a kind of a state. The next term is reward. So a reward is the feedback by which we measure the success or failure of an agent's actions in a given state. For example, if you have a video game, then you know that when Mario touches a coin, you know that he wins points. So that's a reward. From any given state, when an agent sends output in the form of actions to the environment, and the environment returns the agent's new state, which resulted from acting on the previous state, okay, as well as rewards if there are any. So if from going from one state to another state, if that is beneficial, then you could be rewarded. So rewards can be either immediate or they can be delayed. Okay, they effectively evaluate the agent's action, whether that action was productive or not. The next term is policy. The policy is the strategy that the agent employs to determine the next action based on the current state. Okay. It maps states to actions, the actions that promise the highest reward. Okay. So policy is all about getting a reward. Okay. What should you do to get a reward? So policy would, do a mapping of different states and what are the actions that you can take at that state, and what kind of reward you can get if you take that particular action in that particular state. So that mapping is policy. Next, we have value. The expected long-term return with discount as opposed to the short-term reward R. Okay, that is value. So value is long-term, reward is short-term. And it is denoted by V pi of S, is defined as the expected long-term return of the current state under policy pi. So pi is the policy, S is the state, V is the value. and we discount rewards or lower their estimated value the further into the future they occur, right? So we saw a discount factor. Um, and if we are calculating reward, then future rewards are always worth less than the present current rewards. Next, we have Q value. Q value is similar to value, but it takes an extra parameter, that is the current action A. So Q pi is S comma A, which refers to the long-term return of an action taking action A under policy pi from the current state S. Okay, so Q pi is Q value is about not just about state, but also about the action. So it maps all the state action pairs to different rewards. So this is note the difference between Q and policy. Policy is something else because policy is about knowing everything with what kinds of rewards you can get, but Q is sort of a quantity that you can calculate. The next thing is trajectory. So a sequence of states and actions that influence those states. So it comes from the Latin word trajectory is coming from some Latin word that means to throw across. Okay. The life of an agent is but a ball tossed high and arcing through space-time unmoored, much like humans in the modern world. Okay. And that's why when we talk about trajectory, it is some type of a sequence of states. And you can have this sequence and maybe create a sort of a line showing, what is happening at each state to the agent. That would be trajectory. Now, since we have seen the reinforcement part of deep reinforcement learning, now let's take a look at neural networks part of deep reinforcement learning. So neural networks are function approximators, which are particularly useful in reinforcement learning when the state space or action space are too large to be completely known. Okay, so we know that usually the states and actions are finite, but if you have a huge state space and action space and you don't know it completely, then you could use neural networks to do approximations. A neural network can be used to approximate a value function or a policy function. That is, neural nets can learn to map states to values or state action pairs to Q values, okay? So rather than use a lookup table to store, index, and update all possible states and their values, which would be impossible if you had a really large problem, you could train a neural network on samples from the state or action space to learn to predict what will be the value of that according to your reinforcement learning. And like all neural networks, they will be using coefficients, which are, bias or weights, to approximate the function relating inputs to outputs. And their learning consists of finding the right coefficients or weights by iteratively adjusting those weights along gradients that promise less error. So this is something that we already know because we've seen in our previous videos how weights are adjusted and how bias are adjusted. So rather than using a lookup table, you could just have a neural network. You could train it, adjust the weights and everything, and train it and decide how it's going to do the work. Now let's take a look at some real life applications of DRL. So this whole concept of DRL, which is deep reinforcement learning, started with the AlphaGo game, okay? Go is a board game, and AlphaGo defeated the best professional human player in the game of Go. So this particular thing, AlphaStar beat professional players at the game of StarCraft 2nd. OpenAI's Dota 2 playing bot beat the world champions in an esports game. So game playing is one of the real life applications of DRL, but that's not the only application of DRL. Okay. So another one is driverless cars, where again you can use deep reinforcement learning. In manufacturing intelligent robots, which are trained using DRL to place objects in the right position. Okay, so this could help you to reduce labor costs and increase productivity because instead of human beings, you have robots that are going to place objects in the right place. Another popular application is dynamic pricing, which allows you to change prices of different products based on demand and supply. Also, if you have a recommendation system, then you can build a recommendation system according to users' behavior, which changes continually. In today's business activities, DRL is used in supply chain management, demand forecasting, inventory management, handling some warehouse operations, etc. DRL is also widely used in financial portfolio management, predicting and trading in commercial transaction markets. And it is also commonly used in several natural language processing tasks, such as abstractive text summarization, chatbots, etc. Right? So we know about chatbots, we know what they do. Abstractive text summarization is nothing but, creating a summary out of a text. So, you could be reading a 500-page book and you could create a summary of that in just 5 pages. That is what text summarization is. And you could use DRL to do that in natural language processing. You could do abstractive text summarization. You could also create chatbots. So those are some of the real life applications of DRL. And I hope you understood all this. I'll be back with the next video. Thank you for watching.